I'm not used to PowerPoints. I like doing things in person. I'm sorry if this is a really plain, ugly looking thing. I really, really apologize. And if you guys ever want to do something in person, let me know. I'm always open to that. Very interactive. Okay, so the first thing I kind of want to talk about, again, I'm kind of copying Dr. Fondufe's, not copying Dr. Fondufe's slides. I'm copying the same element in a sense of how she's formatted everything, so going through it as an outline. The material is basically the same. I've, though, reworded it so that it's in my interpretation and could be easier for you guys to understand. So let's start. Atomic weight versus mass number. Can anyone tell me what the difference is between these two? Shout it out if you want. Just tell me, what's the difference between atomic weight versus mass number? So
atomic number is, I think, the number of protons and neutrons, or I think it's number of protons and electrons, and then the mass number is, I'm not sure what that is. I don't remember actually.
Oh, I was thinking opposite. I was thinking mass number is protons and neutrons, and atomic weight is everything like together.
Yeah. The second, so first person, very close, nice try, that's okay. The second person who just answered, yeah, that is correct. So technically speaking, atomic weight is the average of the mass number of isotopes in their normal occurring proportions. So that's a really weird statement in my opinion, but what she's basically saying is this, is that if I have these carbon isotopes, right, you can have carbon 12, carbon 13, carbon 14. Now let me ask you a question. Carbon 12 is the most occurring, right? You will always see carbon 12 at least 98% of the time. So then where's the rest of that 2% coming from? Well, you're going to see either carbon 13 1.1% of the time, or you'll see carbon 14 the remainder. So what she's saying is that when you take the average of these mass numbers of isotopes, I know it's a really weird way, I just took the definition that was in the slide. What she's saying is that the atomic weight is going to be more closer to carbon 12 because you have more of that. You have like 98% of this, 1.1% of this. Okay, so it's saying that, and by the way, if you have questions, you might want to unmute yourself because I can't see it, right? So if you have a huge abundance of carbon 12, right, like we said, okay, you obviously have a little bit of these rare isotopes of 13 and 14, but when you take the atomic weight, it's going to be closer to 12.07 AMU. Like if you go on the periodic table right now and you tell me what is the atomic weight of carbon, it's 12.07, right? Because you have more carbon 12. This 0.07 is just coming from these rare isotopes. It's pushing it up.
Does that make sense? How did you calculate that? Like, is that going to be on the exam? Is that something she's going to ask?
No, it's not on the exam. That's
okay.
Yeah, don't worry. That would be that'd be insane a bit for cell bio. I'm just saying it because a lot of people don't understand it or they haven't taken Gen Chem 1. So that's kind of my way of explaining it. Now, if I was in person, 100% I'd be able to explain this a little bit better because you'll be able to see my face and my reactions. I've noticed that really makes a difference. So if this doesn't make sense to you, we can talk about it after. But that's what I wanted to say about the atomic weight. You're just taking the most abundant one, and that's essentially the atomic weight. It's what you find on the periodic table. You're not going to find that anywhere else.
How did you know that was the most abundant? How do you know C12 was the most abundant?
Well, I know C12 is the most abundant because if you think about it, well, again, I'm a senior, so I've seen a lot of I've seen carbon 12 a lot be talked about, and what they always stress about carbon 12 is that the mass of it. So the mass of it is 12, right? 12 AMU, atomic mass units. That's usually how you write it, right? So that's the mass number, and then I can't remember what the atomic number is for this. It's probably, I want to go with 4. I really can't remember. I'm so sorry. But what I'm saying here is that the mass number is 12. you see carbon-12 everywhere. I mean, it's in the soil, it's in our, it's everywhere. But then you have carbon-13, okay? Then you have carbon-14. These are rare isotopes. The reason why they're 13 and 14 is because they have a difference in neutrons, okay? You're not going to see these all the time. You're not. But the whole idea here is that the atomic weight is taking the average mass number of all isotopes. It has to take all of these isotopes into consideration in order to get that value. So if you have this occurring 98% of the time, and you have this occurring like 1.1% of the time, and this one's like less than that, right? If I take all of this together and I just want to find how much does carbon weigh, it's going to be 12.07 AMU. Do you notice how that's closer to this one? It's closer to this one and not to this. It's not close to these ones. And that's because you see this 98% of the time. So it's going to be closer to that. Does that make sense?
Okay, yeah, we'll get there.
Yes.
Yeah, that's okay. If you have other questions, just ask me towards the end. I think honestly, don't stress this. Really, don't stress this. Honestly, I didn't think that would be stressful. I'm so sorry if it was. The next thing I was going to say was this mass number. Mass number, you do not find this. Typically, you will not find this on the periodic table. What I mean is that if you have, let's say, carbon-13, right? This is carbon-13, okay? You're not going to find 13 as the mass number on the periodic table. Why? Because it's an isotope. So it's like a mass number is just adding the protons and the number of neutrons. Your neutrons can always change, right? If your neutrons can always change, then you're probably not going to find that specific rare isotope on the periodic table. You'd find the most abundant one, the regular one. Does that make sense? That's really what mass number means.
Yes.
That makes sense? Okay,
Yes.
cool. If it doesn't, I can like literally pull up the I can pull up the periodic table at times. Just let me know. So yeah, mass number is very specific to an isotope. It's not usually the general one. You usually have to calculate it. That's why there's a whole, you're not going to find it on the periodic table, okay? It usually has to do with isotopes because your number of neutrons is changing. Does that make sense? All right, okay, perfect. Okay, isotopes. I kind of went over it, right? It's a difference when you're counting the neutrons, okay? That's where it differs. You're counting different neutrons. If you have different neutrons, you're going to get a different mass number. That's literally why you have carbon isotopes, which is what I said, right? Carbon-12 has 6 neutrons. That's the regular. That's what you find on the periodic table. Carbon-13 has 7 neutrons. Carbon-14 has 8 neutrons. You do not see these two on the periodic table, okay? They're not normal. They're very, very rare. The reason why they're rare is because your neutrons are different. If you asked a question, by the way, I can't see it. I'm so sorry. Sorry, because I can hear the dinging on my side. So let me know and we can get into it. Now, the next thing I did want to touch on, because Dr. Fondufe did mention this, it's called radioisotopes. So really, when we talk about radioisotopes, and if you were in my 1030 section, I did explain what it was during class. A radioisotope, when you think of radioactive, everyone, I think of bombs. Unfortunately, that is what I think about. Give me one second. I see somebody is probably asking questions in the chat. So I need to be able to see that. So give me 1 second so I can see. Isotopes are things that are unstable. When we think about radioisotopes, I saw somebody wrote something about the nuclear plants. Yeah, that's basically what it is, right? Radioactive. We're talking about these really unstable things. That's why I don't like thinking about this, unfortunately, but you think about bombs, right? I mean, they're radioactive. They are unstable. When we talk about radioisotopes, those are unstable isotopes. They're reactive. That's really what it means. I can even say unstable usually means reactive, okay? That it's not stable, so it's reactive. Now, radioisotopes, typically what we're saying here is that it's the energy that we have, right? Radioisotopes, radioactive, anything like that is going to give off energy. And that energy is typically given off in the form of alpha, beta, gamma radiation, right? Y'all have heard about gamma radiation. That is really penetrable radiation. Like, God forbid, like no one really wants to be in that shape. Like, you do not want to be in anywhere near gamma radiation. Now, the next thing I'm going to say here is that radioactive decay. Can I just ask you guys, what do you think radioactive decay is? If you were in my 1030 section, you definitely know what it is. Can anyone?
I guess whenever it's just like slowly going away into other elements or just like slowly decaying. I don't know how else to explain it.
Yeah, no, honestly, you explained it. You totally explained it fine. Like, really, radioactive decay is what it says it is. You're decaying this radioactive substance, right? But here's the thing. If I have something, let's say uranium, y'all know that depending on the neutrons that are there and the isotope it's in, uranium, it can be very radioactive, okay? And if something is very unstable, if something is super unstable, typically you want to be able to get it back into the stable form, okay? You always want something to be stable. So in order to do this process, you have to do radioactive decay. Radioactive decay. Now, when you decay, you're basically going through a bunch of steps, okay, to get to that stable product, to the last stable element that isn't radioactive anymore, okay? And when it does this, it actually gives off these radiations. So what am I saying? What I'm saying is that let's say you have this, oh, my bad. Let's say you have this unstable A, okay? A is really, really unstable, okay? So it's going to go through some sort of decay process. Have any of you guys heard of alpha decay, beta decay, gamma decay? Have any of you guys ever heard of that?
Yeah.
No.
Yeah. No? Okay. So if you haven't heard of it, that's okay. If you have heard of it, then you probably know what I'm talking about here. If I have A, right, I can make this thing go through alpha decay. What alpha decay is, guys, is basically releasing alpha radiation. I mean, does that kind of make sense? It releases alpha radiation, okay, so that you can get to product B, which is a little bit more stable than A. Now you can go maybe to another type of decay process, okay? Because remember, you're trying to go from the most unstable right here to the most stable. And it has to go through these radioactive decay processes. It has to go through these types of decay, okay? The first decay here was alpha decay. Maybe I'll go through a beta decay next. When you go through beta decay, you're going to release beta radiation, okay? When you release radiation, everyone, you become more stable, and maybe you get to C. C is much more stable. Does that make sense when we talk about radioactive decay?
Does it always go in that order specifically? Or
Nope. No,
okay.
it does not. Like, I could have started with gamma if I wanted to. There's a lot of different types of decay. These are not the only ones.
But
But
all
you're not going to...
alpha, beta, and gamma, they're all unstable.
I mean, typically, so alpha, beta, gamma, it's not that they're unstable. It's that it's a type of radiation that gets released from an unstable element, an unstable atom. It's just the radiation, okay? That's what it's released as. Alpha radiation is what is released from the unstable atom. So you can't really call alpha radiation unstable because that's not really what it is. It's the atom itself that is unstable, which releases that radiation. Does that kind of make sense?
Yeah.
You want to give off enough energy so that you can become stable. If you have too much energy, it's not really good, right? So to get rid of that energy, you have to release it as radiation. You just get rid of it. Does that make sense?
Yeah, it makes sense.
Okay, awesome.
I have a question. Do we need to worry about why is an isotope unstable or no?
Why is an isotope unstable? I mean, why is an isotope unstable? I mean, typically,
If it's
really,
something that we're going to cover later in the chapter, don't worry about it because I don't want to get ourselves out of what we are up to right now.
yeah, no worries. I can answer that after. Is that okay?
Yeah, of course. Mhm.
Okay, awesome. Let's go ahead to the next slide. Okay. All right. I remember somebody had asked this question in 1030 section because that's the one I LA for. Orbitals. Yeah, right? Okay, that's what I figured. So orbitals, okay, if you haven't taken general chemistry yet, you might be confused, like, oh my goodness, I don't know what orbitals are. I don't know what electron shells are. And that's okay. If you need to like come during office hours, that's totally fine. I'm just going to explain it very briefly. Orbitals. When we think about orbitals, guys, if you've taken Gen Chem 1, Gen Chem 2, or not even 2, you're probably in 2 right now. Orbitals are basically where do you find electrons? Like you have to tell somebody, hey, I need to know where this electron is, and you'll be like, oh, it's in this orbital. That's a pretty good explanation. Do you know why? Because 90% of the time, that is where you're going to find the electron, in an orbital. And it makes sense. Why do you think somebody would say, oh yeah, the electrons are in this orbital? Well, first of all, it's because 90% of the time you'll find it there. But also, it's only it only has 2 electrons in it. It's not like there's 50 electrons and you have to find which electron is in the orbital. There's only 2. It's so easy. Does that kind of make sense? Orbitals are used to describe where are the electrons, where are they found. And because you find them, because there's only 2 in that orbital, 2 electrons only, you'll be able to find it 90% of the time. Does that make sense? What an orbital is. You need to remember this, that it is always going to be occupied by 2 electrons max.
Is this like the first shelf of the first shelf that we have around the atom, I believe?
Uh-huh.
Which
Okay, so yeah. So listen, orbitals are really weird, okay? Because let's say you have, I mean, I'm pretty sure y'all are familiar with hydrogen, but it doesn't matter. We can even use helium if we wanted to. But let's just, for example, say this is some nucleus, okay? You guys know that you have these shells surrounding it, okay? You need to know one thing. These are energy shells. What I've just showed you in red is an energy shell. It is not an orbital. I know you're probably thinking an orbital is something that goes around and around and around. No, that's not an orbital, okay? In this setting, that's not what an orbital is, okay? These are called electron shells. What I'm drawing for you right now, these are called electron shells, not orbitals. In each of these electron shells that I'm drawing a pointer with, you will find orbitals in it. It's very weird. So do you see right here? I'm just going to show you this example because somebody just mentioned right here the first shell is where you have 1 orbital, right? Somebody said that, am I correct?
Yeah.
Right? Okay. So if this is the first shell and you have 1 orbital holds 2 electrons, it's just saying this, right? Holds 2 electrons. 1 orbital holds 2 electrons. That's the first shell. The second shell says this. You have 4 orbitals, holds 8 electrons. I just want to know, does this confuse you or no? Does this confuse you?
I think this is where I get a little confused because in
Yeah.
the first part it says it's occupied by 2 electrons maximum, but then it says 8 electrons in the second shell.
Exactly. This is what I'm going to explain to you right now because I knew when people were like confused, I was like, okay, I got to go through this. I'm going to show real quickly to you. I know you can see my screen right now. I'm going to go ahead and show you guys the periodic table. That will make a lot of sense to you. Are you guys familiar with SPDF configuration? Have you heard of that?
Yes.
Yes.
Yeah. Okay, so you guys have heard of that, SPDF. All right. So I'm going to pull up SPDF for all of you guys right now. Let's see. And this is a really good image of it. All right. So if you want, write this down, okay? This will help you right now. And even I'm going to open up my OneNote so that we can start taking notes together, and it'll make it easier for you as well. All right. Sorry, everyone. But really, the way you're going to understand it, because everyone got confused on that second point. I was in class and I was like, oh, they're going to get confused on this. Sorry, this is from some of my other stuff. Okay, let's see. Let's go new page. Okay. So we're going to go ahead and talk about, so we already know what an orbital is, right? Explain to me, how many electrons are held in one orbital?
2.
2. Yep. 2 electrons. Now let me ask you this. What's an energy shell?
It's where the electrons sit. I don't know.
Yeah. I mean, yeah, sure. Why not? I mean, it's basically these big round shells, right? That's what it is. So now you have to, you got to think just a little bit outside the box here, because if I was in person, I think I would have been able to explain this much better. Okay. So we know that when we talk about this first energy level, right? This is the first energy level. Let's call energy shell also N, okay? That's what it means. Energy shell basically is equal to N, okay? I'm setting it as a variable because that is what it is. It's usually called N. When you look at this first one right here, okay? We're going to call that N equals 1. Energy shell 1, okay? In energy shell 1, what it's saying here is, I'm going to come back really quickly to this periodic table. 1. I told you guys 1. Look at this shell right here. 1 and 1. Do you see where I am right now? 1. This is the shell that we're in right now. 1. You can see it right here. Do y'all see the 1, right?
Yes, I see it.
You see the 1.
Sorry.
Okay. You see the 1. No, that's okay. So you see the 1, okay? When we talk about the periodic table, I think you can see this image here. We have these things called S block, D block, P block, F block. Okay, you have all these blocks, all right? Whew. These blocks are typically called sublevels, or we call them subshells. Subshells. So, don't get confused on me, okay? Now we have a thing called subshells. You can also call them energy sublevels. You can call them sublevels. It doesn't matter. Okay, that's what you can also call them. That's like calling this an energy level. It doesn't matter. Okay, it's just like a little small part of this big energy shell. Okay, so you can have, if this is again, okay, I really want to make sure I'm kicking this thing so you understand. If this is my energy shell, okay, this is my energy shell, I will have a bunch of subshells within this. I'll have a lot of subshells in here. So what I'm saying is that you can have a lot of S's in one subshell, in subshell 1. Okay? Now, if this is N equals 1, this is N equals 2, right? Because that's energy shell 2. This is energy shell 3. I'm just telling you, if you have one energy shell, then you're going to have a bunch of subshells within that. And you'll have another bunch of subshells within here. These are not electrons. I'm just trying to tell you that there are levels within one shell. Okay? Does that make sense so far?
Yeah, we're
I'm just arbitrarily very abstract. It's an abstract drawing. This is not correct in terms of, if we're talking biologically speaking, no, it's not. I'm trying to show to you abstract wise so you can understand it in layman terms. Now, you have to understand something here, okay? I'm really trying my best to explain this to you because I know some people don't come from Gen Chem background. The reason why, okay? Remember I told you that you're in, again, God, I really hate when drawings are ugly. If you're in N equals 1, right? This is your energy level 1. If you're in energy level 1, look at the periodic table real quickly. Where do you see the 1? The 1 is here in this area right here. This is the first layer, 1. Okay? I'm going to ask you a question. if you count how many blocks are in this, you count 1, 2, right? Did you count 2 blocks right here?
Yeah.
1, 2.
Yes.
Okay. Listen to me very, very closely, okay? For every 2 electrons you have, that is equal to 1 orbital. Just make that a thing in your head. For every 2 electrons you have, that is 1 orbital, okay? If I want to find out how many electrons are in this energy level 1, I can just go to the periodic table, look here, okay, find wherever there is a 1. This area here is 1 and 1, right? That's 1. And I need to find out how many electrons are in it. I'm going to count the blocks. 1, 2, okay? I have 2 electrons in energy level 1. If I have 2 electrons, that means you have 1 orbital. You already understood the first point, which was, oops, that's literally in the slide right over here, right? That's the first part right here. Now I'm going to talk about the second shell really quickly. Then the rest of them will make sense. The second shell is saying you have 4 orbitals holding 8 electrons. So what does that exactly mean? She's telling me I got 4 orbitals and they're holding 8 electrons. Okay, let's do this. So 4 orbitals hold 8 electrons when we are in the second shell. So she's focusing only on the second shell. So I'm going to draw the second shell for you. Okay, so let's go into a different color blue. This is the second shell. N equals 2. She's telling me that, okay, in this shell, okay, N equals 2, you're going to have 4 orbitals, okay, and you're going to have 8 electrons, right? That's what she's telling me. I'm going to show you where that's coming from right now. If I open up the periodic table really quickly, let's open it up if it wants to. Okay, look at it like this. If you are in the second shell, okay, can you tell me where you see 2, right? 2 is right here. Am I right? Do you see the 2?
Oh, and you're going to count those blocks?
Yes, ma'am. You're going to count those blocks, right? If you count those blocks, okay, just look. 2s, 2p. I'm going to count it. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 electrons right there. Boom. That's what she's talking about. That's what she's talking about when she says you're in the second shell. You need to take into consideration every 2. Okay? That's why she's saying that. So if I go here, okay, so I have 8 electrons and I have 4 orbitals. 4 orbitals. Okay? Now you know that 1 orbital, as always, 1 orbital is equal to 2 electrons. So all it's saying is that if you have 4 orbitals, 1, 2, 3, 4, I'll have 2 electrons in each. And that all of this is in here. So it's saying that you'll have 1, 2 here, 1, 2 here, 1, 2 here, 1, 2 here. Now, when you look at a diagram, that's why these 2 are technically very close together. Why? Well, it's easier to group as an orbital. Does that make sense?
Yeah, it made it a lot easier. Thank you.
Yeah, of course. I know it was kind of rough when I was explaining it, so I really apologize for that. So let's go ahead real quickly and complete the rest of this. I like to write my notes on the side so I know what I'm teaching. All right, so I just actually explained to you myself why you have 4 orbitals in the second shell. But you guys understand it, right? You understand now why you have 4 orbitals and why it's holding 8 electrons. Made sense?
Yep.
Awesome. Let's go to the next one. Okay, so this one's a little bit interesting. We're going to be talking a little bit about the valence electrons, okay? So let me just ask you, valence shell, what's a valence shell? Just somebody tell me. What do you think it is? What does it hold?
It's the outermost shell that holds the outermost electrons.
Yes, ma'am. And can you tell me, like, yeah, that's definitely correct, right? Number of electrons in the last shell. What you really need to also know about valence electrons is that those electrons in that outermost shell, it's going to tell us how that atom is behaving, okay? So, and I'll get into that in just a second, right? How that atom, how that element is behaving. Now, when we talk about something being stable, what does that actually mean? What does it mean in terms of that valence shell? How many electrons would you have if something is stable?
I think it means when it's valence, it means that it's when it's stable, it means that we have 8 complete electrons in our last shelf.
Exactly. And when we say something has 8 electrons, we like to call that an octet, okay? When something is an octet, it basically, yeah, it's full, like what you said. It has all 8 electrons. It's full, okay? It's good. It is stable. It has all the electrons it needs to be chill, really. That's what it's saying. Now, when we talk about something being reactive, what exactly does that mean? Like, what can you think about when something's reactive?
I think it means like one of the electrons are single.
Yeah, so
When
when
it
we talk, oh yeah,
when
go ahead,
it's
somebody.
when it's trying to gain 8 electrons is when it's reactive.
Yeah, exactly. So typically when we see something being reactive, you don't have a full set of 8 electrons, right? So it's usually that outermost shell. It doesn't have 8. It doesn't have 8 electrons. And if it doesn't have 8, it's going to be reactive. It's going to want to, not that it's going to want to take, but it's just going to be reacting with something else to either fulfill that or to give it away. Okay? And we can get into that towards the end if any of you guys don't understand. And then, of course, Octet Rule. I mean, I kind of explained it again. Just someone say it.
When we have 8 electrons in our outer shells.
Yep, perfect, right? So let's just do it. 8 electrons, right? So now let's look at this diagram that I have right here. Okay, if you look in this group 1, right? Group 1 has hydrogen, lithium, sodium. Now, if you look at group 8, that's helium, neon, and argon. What do you notice? Don't look at helium because this is a funny one because technically it doesn't have 8 electrons. So look at neon, argon, okay, and don't look at hydrogen. Well, you could look at hydrogen if you wanted to, but let's just stick with lithium, okay? Compare lithium and compare neon. If you compare these two, you will see that lithium has 1 electron and neon has 8 electrons, right? You guys know that group 8 is usually called the noble gases. I mean, there's 8 electrons. It's not going to react with anything because it is stable, okay? If it's stable and it has electrons, it doesn't need any more. Does that make sense? This is group 8. We're good with that, right?
Yeah.
Awesome.
Yeah.
But now, let's make this a little bit neater because my handwriting really do be a little ugh. So let's say we have sodium, okay? And let's look at chlorine. This is interesting, and we're about to get into it. But when something like this, sodium and chlorine, get together, this is pretty reactive, right? 1 electron only. And this one has 1, 2, 3, 4, 5, 6, 7. It only needs 1 more electron till it becomes 8 electrons and it becomes stable, right? If I put Na, right, with Cl, that Cl is going to grab that last electron and it's going to become stable. That's what we call an ionic bond, actually. And I will get into that, but I just wanted to show you that you see how things are reactive when it has 1 electron? Something that might need it, like chlorine, has 7 electrons. It only needs 1 more till it becomes stable. So what will it do? Well, the sodium's pretty reactive, only has 1 electron, so chlorine will come in and grab that electron. Do you guys understand how that reactivity kind of idea worked here?
Yeah, and when you're saying it
Yes.
grabs it, it means like it's sticking together. Like it's not like taking it and running off to like separating.
Well, yeah. Basically, I mean, when you put NaCl together, you're making a bond, right? And when you have bonds, typically ionic bonds are transferring. I wouldn't say it runs away with it. No, I don't think that happens. Really what it's saying is that it sticks together because chlorine wants that one electron so badly that that sodium is going to kind of transfer it towards it. I can get into that a little bit later, but that was a really good analogy, running off with it. I wouldn't say it runs off with it because it is binding, not running away. Does that kind of make sense?
Yeah, that makes sense. So obviously the chlorine becomes like the full octet, right? Is that considered like the full octet since it has 8 now?
Well, that's the thing. It can't really be considered a full octet because how I see it, a full octet is usually something that is stable. We're talking about
On its
these
own,
noble
right?
octets. Yeah, we're talking about it on
Okay.
its own, right? But in this case here, if I have a, let's see, 1, 2, 3, 4, 5, 6, 7, right? That's chlorine. I have Na, has only one valence electron, right?
Mm-hmm.
So the problem here is that this chlorine really wants that, like, basically wants that electron. So when you bind with something like this, usually it's going to kind of grab, I want to say it's going to grab this a little bit, and then it's going to create this, like, it's going to create this little, it's going to create an ionic bond. It's electrostatic. It's a little bit dense, actually. I can talk about it later, but you kind of see what I'm saying? It makes this thing, it makes a bond, really.
Yeah, I see
Because
that. I get that.
you get it? Okay,
Yeah.
cool. I can totally answer it later.
A question there.
Yeah.
So once they're bonding together, are they considered a molecule?
Yeah, they are
Okay.
considered a molecule. Yeah, because I mean, NaCl is technically table salt. That's a compound. And if you notice there, Cl didn't run away with the electron. If it ran away with it, you'd never have salt. So it's really bonding together.
Okay. Yep, makes sense.
Awesome. Okay, so atoms bond to form molecules. Okay, so here really what I'm saying is that don't worry about this picture yet, okay? So covalent bond. Can somebody explain to me what a covalent bond is? What a
Oh, I
covalent
don't think they're sharing electrons. I think ionic is sharing. Or am I opposite?
opposite. Yeah,
So
you're opposite.
covalent is sharing and ionic is not sharing.
Yeah, it's
Yeah,
kind
okay.
of weird, but yeah, you kind of get it. I actually wanted to say something real quickly. I think this makes it look like it's sharing. It's not sharing. It's actually an electrostatic attraction between them. So they're just very attracted. They bind. Okay, see, even binding is a weird word for me to use here. When you have NaCl, okay, this is an ionic bond, okay? Ionic bond is an electrostatic attraction. It's not sharing electrons. This is not a covalent bond. It's an ionic. Ionic is electrostatic, so it's just attracted to each other. Do you see what I'm saying? I wouldn't even say it's bonding. I would say they're very much attracted to each other, where chlorine kind of pulls that electron sometimes towards itself. It pulls it because it wants to be 8, but it never, it's, does that kind of make sense? It's an electrostatic attraction, really.
Um,
So an ionic bond is like an electric attraction.
Yes, it's an
So
electrostatic.
or opposite attraction.
Yeah, when you say opposite attraction, what do you mean?
Meaning that chlorine is a negative charge and sodium is a positive charge. So then they bind together as a buddy system.
Exactly. Yes, ma'am. That is correct. It's like this. I didn't want to write it yet because I didn't know if I was going to confuse people. But yeah, you have this positive area, you have this negative area. That is exactly what it is. It's an electrostatic attraction, positive and negative. Okay, sorry. Kind of got ahead of ourselves here. Okay, so covalent bond is when you're sharing electrons. Okay, you're sharing electrons between elements. How I like to think of a covalent bond is usually when you have a non-metal plus another non-metal. That's really how I see covalent bonds. I mean, that's just generally how I see a covalent bond. It's some sort of non-metal with another non-metal. Ionic bond, on the other hand, would be like a non-metal with a metal. Now, physiologically speaking, covalent bonds are technically stronger than ionic bonds. If you've taken chemistry, you've seen ionic being stronger than covalent. And if you've been in class, Dr. Fondufe also mentioned that a covalent bond, physiologically speaking, is going to be much more stronger than ionic. We're not talking about the chemistry reaction here. We're talking about the physiological version. I could probably talk about that later, just because I don't want to get too ahead of myself here. But now, I'm going to ask you a quick question. Hydrogen, how many covalent bonds do you think it could make?
Just one.
Exactly, yeah, just one, right? So really, this thing right here, when it says valence, valence basically means your combining capacity. So it's saying what is the combining capacity that an element has to like combine with another element, right? So what it's saying is that if I have carbon, okay, and I have hydrogen, if I want to like bond these two together, okay, actually let's make it even a little bit more easy, okay? Let's say you have does everyone know how to draw Lewis dot structure? By curiosity?
I don't.
Curiosity? You don't? Okay, then that's okay. That's okay. Let's say you have two hydrogens that are coming together. You guys know that hydrogens are nonmetals, right? That's why they're technically covalent bonds. If I want to make a bond with each other, notice it only makes one, right? The valence for hydrogen is that it can only make one bond. It is saying that your valence is one, meaning that you can have only one bond really made with another element to create a compound. This compound makes hydrogen, right? Hydrogen gas, right? Usually it can be in a gas form. It's saying that your valence is one because you can only make one bond with something else here. Now, if I want to look at carbon though, carbon has a valence of 4. So what does that mean? It's saying that your combining capacity, your valence, right? Valence basically means, let's just write it here, valence basically means your combining capacity, okay? So if I want to combine with another element to make a compound, this is how many bonds you can make. Oops, you can make 4. So it's saying that if I have carbon and I have 4 H's, I have 4 H's surrounding it, 4 hydrogens, okay? Basically, you can make methane gas. I don't know if you've ever heard of methane gas. Do you see that? I just put 4 hydrogens around it. Well, that's the valence for it, right? It can only make, that's the combining capacity, okay? Does that make sense?
Yes.
Yep.
Awesome. Okay, let's go to the next one. Okay, atoms bond to form. Okay, so that's basically what I showed you, right? I showed you the hydrogen, okay, H2. I showed you this, right? The combining capacity is 1. You are making one bond. That's why you see it here. Let's go to methane. I see methane here. Oh, my picture got cut, but it's basically had 2 hydrogens here and H. Oops. So you see that, right? I don't have the H written, but that's the H. If you look at carbon, 4 bonds were made. You see it right here. 1, 2, 3, 4. Right? You even have it here. 1, 2. That thing wasn't showing. 3, 4. Do you see it? Makes sense, right? Your valence is basically the combining capacity. It is how many bonds you can make. How many covalent bonds you can make. Good?
Yes.
Yeah.
Awesome. Okay, so now we're just going to quickly talk about how basically atoms form molecules. It's same thing, concept 2.2, right? So now here's the thing. Covalent bonds are known for sharing. That's what we said, right? You're sharing electrons with each other. Covalent bonds, again, are typically from non-metal plus a non-metal. So if I pull up the periodic table, y'all know where the non-metals are, right? I'm going to assume yes? Okay, cool. So if you know covalent bond is non-metals plus non-metals, okay? And you know that they're always sharing, well, they're known for sharing, but you're not always going to be able to share. Why do you think you're not going to be able to share? Does anyone know what it is? What can cause something to not be shared equally between each other? Because here,
Being more electronegative.
Yeah, exactly, right? So what does electronegativity mean then?
I think that means that one atom has like they're attracting the electrons more to their nucleus compared to the other atom that they're with.
Yep, yes, ma'am, that is correct, right? So what we're talking about here is that you have something, some atom is much more stronger. It wants electrons very badly from the element or atom that it is near. So here we have the periodic table, okay? This is a good indicator. You should know that as you go up this direction, you have very high electronegativity here, very low electronegativity here. What does that mean? That means if I pair fluorine, okay, with maybe barium, okay, if I combine these two together, 100% fluorine will try to pull all the electrons that barium has, all of the valence electrons particularly, to itself. It wants it, okay? That's what it's saying. It's saying that I'm going to pull as much as I can from you. If something pulls something by a lot, if fluorine is pulling all the electrons that potassium has or calcium has, strontium, right? Magnesium. If fluorine pulls all those electrons to itself because it's attracting it, okay? What happens then? What happens to that bond?
Is it stronger?
Well, stronger in a sense of like the attraction being stronger.
Yeah.
Okay.
Or maybe it's stable now, since it took all the. Maybe I
Okay.
don't understand.
No. That's okay. That's totally fine. Those are like valid answers. I can see why you said that. But really, when we're talking about well, when we talk about something pulling electrons towards itself, have you heard of the term polarized? Polar? If something's polar, it's pulling itself. Okay? That's how I see it. So really, if fluorine, this is not going to be technically drawn. Let me put H2O, okay? If I have H2O here, okay? Can I ask you a question? Is oxygen pretty electronegative compared to hydrogen?
Nope.
Yes.
Yeah, it is definitely.
Is it?
Yeah.
I said yes.
Yes, it is. It definitely is. It definitely is more electronegative. So if something's more electronegative, what's going to happen here is that this is going to pull it, right? Oxygen is pulling the electrons that hydrogen has, right? It's pulling it. If it is pulling it, well, what we're going to say here is that this thing is going to be called polar. It's polar. Has anybody heard the term that water is polar? Water is polar.
Yeah, but I don't really understand polar and non-polar, to be honest.
Okay, it just if layman terms, I'm about to explain it and hopefully it makes sense. Give me 1 second. I'm literally about to hit it, right? So that's what we're talking about, right? So we're talking about non-polar, polar, ionic bonds, hydrogen bonds, van der Waals forces. Right now I'm going to talk quickly about the bonds. And I know somebody mentioned that they didn't understand non-polar covalent bonds versus polar covalent bonds. I'm going to hit that right now. So non-polar covalent and polar covalent. I know somebody mentioned that they didn't understand it. Is there somebody who could explain to me what nonpolar is though, and maybe help out if you do know it?
So let's say that two atoms are trying to they're both sharing electrons, and the amount of the electrons that they're sharing with each other is equal. Like let's say we have a covalent nonpolar. If it's one pair, they're both sharing 2 electrons. If it's 2 paired, they're all together, they're sharing 4 electrons, which is equal to both of, it's equal.
Okay, yeah. So basically in short, you're telling me that a non-polar covalent bond is when electrons are shared equally, right?
Yeah, you can say that, yep. I think this is...
Yeah, I just kind of summed it up. So yeah, that is what it is. Nonpolar covalent bonds are when electrons are shared equally. They're shared equally. So I'm gonna show you that really quickly. So when things are shared equally, I'll give you a good example, okay? That usually means that the electronegativity is equal to each other. So they're both, example, if I have hydrogen, okay, look at this. If I have hydrogen right here bonded with another hydrogen, can you tell which one is more electronegative or not? Can you?
No.
No.
No, you can't. You can't tell which one's more electronegative because they are technically the same element, right? Hydrogen with hydrogen. This is what you would call nonpolar. You can't differentiate which one's more electronegative. That's what makes it nonpolar, okay? That's one example of nonpolar. It is sharing equally between each other. You can't tell which one's more electronegative, okay? That's one way of saying what is nonpolar. Does that make sense to whoever had asked what it was, what nonpolar was?
Yeah, I get it now. So now it feels like oxygen and hydrogen, then it's polar because something's being pulled and the electrons are not being shared equally.
Yes, you got it, right? Polar
Okay.
covalent is unequal sharing. Okay, that's exactly what it is. It's saying that something is more electronegative than another. Like when we were talking about water, right? When we have water, that O, that oxygen was pulling. It was much more electronegative, especially compared to hydrogen. So it was pulling all the electrons near hydrogen. Oxygen was pulling it, which caused this hydrogen to be less electronegative, right? I mean, technically it is to begin with, but it's losing even more electrons. Its electrons are getting pulled away from it. That's what we call polar covalent. It is unequal sharing. Let me show you an example right now. Okay? Don't get it confused. Let's focus on nonpolar real quickly. This is exactly the same example that I gave with hydrogen. Hydrogen with hydrogen. You can't tell the difference between them. You really cannot. Okay? Now, this one's a little bit more interesting. You see right here we have carbon dioxide, right? This is called CO2 because you have two oxygens and a carbon. This is also nonpolar. Do you think you can guess why it's nonpolar?
Maybe because it's being pulled equally on both sides.
Exactly. Yes, ma'am. It's getting pulled. Oxygen is pulling it. Okay? Because oxygen is more electronegative than carbon if you look on the periodic table. And you'll have notes, so you'll definitely be able to see that, okay, in the periodic table. If you look at carbon and chlorine, well, that makes sense too, right? This chlorine is going to pull all the electrons from carbon. This chlorine is 2. This chlorine is 2. This chlorine is 2. At that point, all the forces are canceling each other. It becomes nonpolar. Yeah, they are equally sharing. Does that make sense too?
Do you think on the exam that we're going to need to know like which elements are more polar or non-polar than, or more electronegative or than others?
Electronegativity, I mean, if she's gone, because I looked at the slides, I haven't seen her exam. I have no idea. I mean, she changes them yearly, so I'm really not sure. If it's in the slides and she has
Like,
talked about electronegativity, like which one is more electronegative than another one, then yeah, that's game.
like she would be like, is oxygen more electronegative than hydrogen? That would be kind of like a question on there.
I
Do
honestly
you
really don't know.
think? I don't know.
I
What does that
do I think?
question look like, I guess?
I
How does
think, I'm sorry. I think if she has mentioned it, like there are some specific atoms that she always talks about. So if she has mentioned it in the class, she might bring it. But I think she wouldn't go to the periodic table and go to like different atoms that we haven't heard of and bring it in and be like, which one is more electronegative? Or even if
Okay,
she
I
brings it,
gotcha.
she might give us like the information about it.
Yeah,
Yeah,
I
so
would check the lecture because I know there's a table 2.3 where she has about 8 elements that has electronegativity that she recorded, but I can't remember if she said that we need to remember it or if it's just something to go by.
Okay,
so
I'll look at the list.
if she gives you a periodic table and she asks you a question which is more electronegative, that is game. She's giving you the periodic table. That's without a doubt she'll give that to you. You don't need to memorize which atom or element is more like where it is on the periodic table. You don't need to memorize that. You'll need to know though the general trend, right? So fluorine is going to be the most electronegative compared to lithium, compared to magnesium, strontium, potassium, right? That's just a trend. So knowing those trends is going to be very helpful for the exam. I know that that doesn't really answer your question of what she's going to ask, but also
No, it does. It answers it perfectly.
It does? Okay, I'm
Thank you.
glad. Yeah, of course. So now, what does it mean to be polar? What does it mean to be polar? I know one of y'all already answered this. Just say it again for me.
It's unequal sharing and more electronegative.
Yes, unequal sharing plus electronegative. Yeah, I know my handwriting is pretty bad here. I did want to do one thing. I didn't hit polar. I'm going to hit it real quickly. Polar is unequal sharing, right? Let's go to this example. This is water right here. Oxygen is more electronegative. Electronegative, so it is going to pull those electrons from hydrogen. That's where you're getting this electronegative sign and you're getting this electropositive sign. Electropositive means that, well, you're kind of losing you're not losing your electrons. You're just getting your electrons pulled away from you because oxygen is gaining them. It's pulling on it. Does that make sense? That positive and negative type feature?
Yeah, it does.
It does. If it doesn't, let me know because I do have a way of understanding that, and maybe might not be biologically right, but it has worked about 98% of the time. So come back to me after class or after this thing and I can definitely explain it to you. So that's what we mean by here. If you look at nitrogen versus hydrogen as well, nitrogen is definitely going to pull those electrons from hydrogen, thus giving you this electronegative sign versus the electropositive. Electropositive is not the best thing, everyone. That basically means it's kind of weak in terms of electronegativity. It means that something with this like symbol on it can just pull it away. So really, if you have electronegative and an electropositive thing, oof, electronegative is going to take that positive. That's what it's saying. Okay? I'm layman terms there. Okay, so this is where we talk about those partial charges that I just showed you. When you have unequal sharing, you're going to get one side that might be more positive while the other side might be more negative. That is what we call a partial charge. Okay? This is the partial charge. And that's what I'm trying to show you. When you have that nonpolar, okay, it is an equal sharing. If it's equal sharing, you're never going to see these signs on it because one way is not pulling more than the other way. In fact, they're equal, right? That's why it's called equal sharing. One atom is not going to pull more than another atom. Now, when we talk about polar covalent, we say unequal sharing. We say that there is a partial charge on it. That is because it is unequal, meaning that, you know how I just told you that this negative, if I have a negative and I have an electropositive, electronegative is going to pull that thing towards it by a lot. Right? If something is very electronegative, like oxygen, like fluorine, okay, it's going to pull from something that is electropositive, okay? And you can see that right here. Look at this big space. It is pulling a lot of electron density towards itself, right? Do you see what I'm talking about here? What it means to be polar?
Yes.
Yes.
Awesome.
Yeah.
Ionic bonds. Okay. We talked about electronegative, but when we talk about something that is so electronegative, okay, and it's binding with another atom, when we have these covalent bonds, okay, covalent, okay, it's usually a nonmetal plus nonmetal, okay, and it can either be nonpolar covalent or it can be polar covalent, okay? So you can get either one of those two, but it's usually nonpolar. When you talk about ionic bonds, my friends, you're usually talking about some metal plus another non-metal. Ooh, that is when I'm talking about this formation by electrical attraction of positive and negative ions. So what am I talking about here? I'm talking about something that is very electronegative, okay, that is binding with another atom. If I put NaCl, okay, remember the positive and the negative ions? Okay, this is what I'm talking about. This is a positive ion. That's an, oh, whoa. This is a negative, okay, I guess, there we go. That's a negative ion. The ionic bond is formed between this metal, and it is formed between this non-metal. And you're getting this electrical static attraction, okay? That's the ionic bond, really. And here's a good image of it, right? Remember that picture I showed you before? How I was like, oh yeah, it kind of looks like this. Looks a little bit like that. I mean, this is what I was trying to show, and maybe I should have done that better instead of grouping the whole atoms. You're looking at this electrostatic attraction right there. You see how, remember, chlorine has 7 electrons, right? This has 1 electron, 1 valence electron. So chlorine, if you go back to the periodic table, everyone, chlorine is much more electronegative, and I'll show you. It is much more electronegative right here. Chlorine is right here, sodium is right here. This is more electronegative, so it's going to pull it. And that's why we see this pulling right here. This chlorine is going to pull it, this electron from sodium, and it's going to give it to there. And then that's when you make this ionic bond, right? Because this is technically having that like octet, right? But it's like, it has that electrostatic attraction to it to have it. Am I making kind of sense here?
Yes.
Okay, great. Wow. I thought I explained that like a little rough, but I'm glad that made sense. Okay, so like I said, talking about salts like NaCl, cations and anions. Does everyone understand what a cation is and an anion? If somebody answers that, I'm probably not even going to hit that.
Is cation a positive charge and anion a negative charge?
Yep, you got it. That's exactly what it is. That's really what it is.
I have
Now,
a question.
Yeah, go ahead.
How does ionic bonds relate to nonpolar?
How does it relate to nonpolar? Well, when we talk about nonpolar, so let me erase all of this real quickly. When you're talking about nonpolar, remember one thing, okay? It's a set of rules. When we talk about nonpolar, this is generally going to be covalent, okay? You're never going to see an ionic that is nonpolar, okay? Because that would entail that there's a sharing happening, like they share equally with each other. But right here, it's telling you that there's an electrical attraction between positive and negative ions.
Oh.
I don't really see that. You see what I'm talking about?
So, so nonpolar and polar fall under covalent bonds, and ionic bonds are just more electrical attractions to each other.
Exactly.
Okay,
Yes,
okay.
You got it. Yep, that's exactly what it is. Okay, that's good. I'm glad you caught it. Yeah, so the other thing I was going to say is that, yeah, cations are typically positive charges, anions are typically negative charges. So you're most likely going to see those nonmetals like chlorine, fluorine, oxygen. They are usually anions, okay? You're going to see cations typically be magnesium, sodium, lithium, barium, things like that. Those are cations, okay? And I mean, I could get into the technical bit of it of a cation is positive. It is usually losing electrons. I'm going to write that here actually. Cations usually lose electrons, and anions are usually gaining electrons. Does this make sense actually? Because you can actually see it in this image right here. If you know that sodium is a cation, right? And you know that chlorine is an anion, right? And you know that anions are gaining electrons, right? You're filling up this electron here. And cations are positive, so you're losing an electron here. You see what just happened, right? Like,
So you know it's a cation or anion by the process, not by anything else?
I mean, there's a lot of ways you can honestly determine a cation and anion. I usually like to think of cations and anions. You're usually 99% of the time going to see a cation and anion in terms of ionic bonds. You don't see that with covalent. You don't, because you have a positive and a negative charge. That doesn't happen. When we talk about cations and anions, it's a little bit different compared to this and this. We're not talking about partial charges. You're literally talking about positive and negative, okay? So when we talk about those positive and negatives, yeah, you're talking about losing electrons and gaining electrons. Literally, like losing it and gaining it. And in that sense, you can see it in an image, and you can also see it in terms of Na or Cl. Does that kind of make sense?
Yeah.
For that type of process, you'd need to know how to draw a Lewis dot structure. And unfortunately, I don't think I should cover that because that could really confuse a lot of people. But hopefully that makes sense.
Yeah, it's okay. Yeah.
Okay, awesome. This is the last part. Honestly, so ionic bonds are transferring electrons. You're not sharing electrons. And I feel like that's I find that a little bit weird, because to me, you'd be like, oh, this looks like it's sharing. Technically, no, it's not sharing it, because you literally are filling up this electron there. You quite literally just transferred an electron there, and you lost the whole shell here. Like, do you see there's 1, 2, 3 shells? If you count this, it's 1, 2, okay? And that's because you gave an electron here. And that's how you get the cation, okay? My bad, this is the cation right here, okay? And this is the anion right here, right? Cations and anions is when you get that positive charge, which is right here. Anion is when you get that negative charge there. The anion is gaining that electron that got lost, okay, and it's given to them. The cation is losing an electron, which literally meant that you lost this whole ring here, got erased. It's not there anymore. Does that make sense?
A question.
Yeah.
It does make sense, but once they're both, I would say, stable, because they all have like 8 electrons now, they're not going to be reacting with each other anymore. So how are they going to be able to make salt? Or what is there that's going to keep them related?
So really, actually, they are still they are bonded, like they are together. I know they have an electrical attraction is equivalent to saying they're binding. An attraction is binding. Like if you like somebody, if two people like each other, they have an attraction, they have a bond with each other, right? That's the same idea here, really. So when you say here, like let me just tell you, okay? So if you have neutral, okay, this is Na and this is Cl. There's no positive, there's no negative charge on it, right? Cl has 7 electrons, needs 1 more electron, right? So let's just say this is person number 2 and person number 1. They like each other, okay? Person 2 wants a little bit more affection from number 1, okay? So chlorine wants more affection from number 1, so maybe let's call this electron affection, okay? So this person, which is sodium, is going to give that affection to chlorine. Chlorine is in love with sodium, okay? As soon as it does that, it loses its own affection, right? Because it just gave the affection to that person, okay? It just gave it. So if it gives it, okay, it gives it, but technically it gave it to that person, but it's still in love with that person, okay? So that's where you get that attraction going, okay? You still have that attraction. Yeah, you gave it, but you still love them. I don't know if that's a really good
Yeah, it was a
analogy.
really strong example.
That was good.
Makes sense.
That was good? Okay, I'm glad. Okay, cool. And then that's where you get this cation and anion, because Na plus, Cl minus. It's saying here that, oh, you just gave me 1 more, great. Like you just get a negative sign for it, and then when you give something, when you lose an electron, it becomes a cation. When you gain an electron, it becomes an anion. You get a negative charge here, you get a positive charge there. That's just kind of a definition type thing. Does that make sense?
Yep, it does.
Yeah.
Okay, awesome. Okay, last two bonds, hydrogen bonds and van der Waals. I'm going to go quickly through this because I think that this is probably very, very easy. Hydrogen bonds, what I think you should know about this is that hydrogen can only bond to 3 elements. It's nitrogen, oxygen, and fluorine. That is it. That is it. Hydrogen bonding, if it is, let me tell you something, if you get a bunch of these, okay, this is all these hydrogens, okay? Let's say all these hydrogens are on this chain of carbons, okay? By the way, I know that this was in your slides. When you have only carbons and hydrogens bonding together, you call it a hydrocarbon, okay? You call this a hydrocarbon. Boom. Let me tell you something. Let me ask you though, is this a hydrogen bonding? Is any of that hydrogen bonding?
No.
Exactly, it is not, because it is not nitrogen, oxygen, or fluorine. You are bonding carbon with hydrogen. That's not a hydrogen bond. That is not what it's called. It's called a hydrocarbon bond, but not a hydrogen bond, okay? Now, one thing here is that is very weird. Growing up, I was taught that hydrogen bonds are very, very strong. But here she's telling you that, nah, the strength is actually a little bit lower, and it's actually weaker than ionic and covalent bonds. Now let me ask you a question. What if you put a bunch of hydrogen bonds together? Let's stack a bunch of hydrogen bonds. Let's put nitrogen, hydrogen, nitrogen, and hydrogen, and you make 5,000 of those versus one ionic bond. Which one do you think is which one do you think is stronger? The stack?
Hydrogen bond?
Exactly, yeah, the hydrogen bonds. The more hydrogen bonds that you have, okay, it is going to be stronger than that one ionic bond. That's just an example, right? We're arbitrarily speaking. So I'll give you a good example. Whoa. I'll give you a good example of this, right? Your DNA, everybody, you know this thing? The double helix? Yeah, the double helix is made by hydrogen bonds. So if it was so weak, wouldn't it be breaking? No, it doesn't, because you have so many of these hydrogen bonds together that's where all the strongness, the strength comes from. That's what keeps your DNA intact. The amount of hydrogen bonds you have, that's what makes this thing strong. That's what makes it, that's what gives it the strength, okay? If I just had one, that's pretty weak, okay? That's hydrogen bonds. When you talk about van der Waals, let me tell you something. Van der Waals is found in everything. It is just to keep the minimum amount of attraction, okay? It is very weak, okay? You can find it in polar bonds. You can find it in non-polar. Let me tell you something. If you have this bond, this is what? This is called a non-polar covalent bond. Let's do an NPC, non-polar covalent. Well, it also has van der Waals forces, VDW. It also has that. Why? Because that is the minimum amount that you need to keep something there. I'll give you a good example of that, okay? So for me, it's like this. When I was in school, I was trying to like glue, I don't know if you guys like the stick-on glues. You know those blocks of glue where you had to like put it all on the back of the paper and then put it on and then you could take it off if you wanted to. It wasn't as good as tape, you know? Do you know what I'm talking about? These blocks of glue like this.
Yeah, it was like purple.
Yeah, right? Okay. I didn't like those. I thought that they kept off, okay? I thought that they were pretty weak, okay? So what I would do is that if this is my paper, I would use this block first. Call that van der Waals forces, okay? And then after that, maybe I'd put tape on it to really solidify it. This is what I would call the non-polar covalent. That thing solidifies it. But in general, you always need this base. That base is what I call van der Waals. Does that make sense? It's just the minimum amount of something you need. Does that make sense?
Yeah.
Awesome. Last thing is redox, and we'll call it a day. That's it. Redox, what do you think it is? A redox reaction.
Gaining and losing electrons. So I think reduce is when you gain the electron. Oxidize is when you lose it.
Yeah, that's correct. Redox is basically you're transferring electrons between two molecules, okay? You're transferring electrons between two molecules, just back and forth type deal. It's usually balanced. I wouldn't say it's unequal, really. And I can tell you why. That's through a redox reaction, you're never going to have like more electrons on one side versus another. That's generally redox. It's usually balanced. You have to go through multiple steps to do this. Now, you mentioned losing electrons and gaining electrons. This is very important, okay? I have a really good mnemonic for you if you really want to learn this. Leo the tiger gurs. So Leo the tiger gurs. When you lose electrons, you are becoming oxidized. When you gain electrons, you are becoming reduced. This is the molecule. The molecule becomes itself is oxidized. The molecule here is reduced, okay? I need to say something because I swear everyone gets this very confused. If some molecule is oxidized, you call it a reducing agent. This is called a reducing agent. If something is gaining electrons, it is reduced, but it is called an oxidizing agent. What I'm trying to tell you here is that, okay, this thing got reduced. This compound gets reduced. So it's going to be an oxidizing agent because it causes this one to get oxidized. This gets reduced, so I am called an oxidizing agent because I'm going to make this oxidized. Okay? Now let me do it for the other side. The backwards way of thinking this is this, that if I'm losing electrons, I'm going to become oxidized. I get oxidized. Well, if I'm getting oxidized, then that means I am a reducing agent because I cause this compound to be reduced. That's why I'm called reducing agent, because I reduce this compound since I'm already oxidized. Does that make sense?
Yes.
Awesome. So that's what I am going to call a day. I hope this made sense. I think I had actually an image here that I could show you. Redox reaction. I can show it to you actually really quickly here. This is one thing that I like about teaching online, is that I can show you guys images really quickly versus when I was teaching in person. It was very hard. So you can see here, this is a really good image of that actually. You have a reducing agent, okay? But this reducing agent becomes, oh, whoa. Honestly, this is a little bit confusing for me to, let me find something a little bit better actually. That was a kind of funky image. Actually, wait. So, okay, I get you, okay? So A to B is becoming oxidized, okay? So A is losing electrons. Remember Leo gurs? So if Leo gurs, let's do something. Copy image, and let's put it here. Let's do paste. Okay, so if I have this thing here, right? Remember Leo gur. Leo gur. So if Leo gurs, then that means that we're losing electrons, which means it's oxidized, versus gaining electrons, which is reduced, right? Oops. Okay, so if this thing here has electrons, right? When it becomes into this thing right here, it lost electrons, right? I mean, these electrons are here. Well, they're not here anymore. So what do we say about it? Lost electrons, we're going to call this thing right here gets oxidized, okay? Now, if I look here, gaining electrons, well, B is right here. It has no electrons. All of a sudden, it gets electrons. Well, if it gains electrons, it's reduced. So this, from here to here, B gets electrons, gains it. So GER, it's becoming reduced, right? Now, remember what I told you. If something is getting reduced, that means that it is an oxidizing agent. And it says it right here. Why is it an oxidizing agent? Let me take this off real quickly. The reason why it's an oxidizing agent, okay, is because, yeah, this became reduced, great. But if this becomes reduced, then what became oxidized? This. I helped oxidize that. That's why I'm called an oxidizing agent, because I oxidized this, and I became reduced. Does that make sense? Vice versa.
Yes.
Awesome. Then that's it. That's all I have for today. I really appreciate you guys kind of sticking out through this. It was a little bit rough, but yeah, hopefully if you guys are down, we can definitely do in-person reviews. I'm much more of a fan of that. It goes a little bit faster in my opinion as well. So I'm gonna go ahead and stop recording, and thank you again. I will post this on YouTube as well. Stop recording.